back and forth. Okay. Okay, that should be an easy one. The tragedy at Lake Neos. So there is no explaining. One person is out to lunch, but there is no explaining in here because we know it was carbon dioxide what killed everybody, right? So it was carbon dioxide that killed everybody. Any questions on that? So likes dissolve likes, right? Non-polar will dissolve non-polar, polar will dissolve polar. Oh, look at Mrs. Spellbrennan. So you could do this by process of elimination. If they are the same, it likely won't happen. If the polarity, what mean the polarity is opposite? What? Polarity is positive and negative. You could have negative and positive, it doesn't matter. And you do want the forces that make the hydrated shell stronger. Now, so we haven't gotten into the interesting part, but we talked about this in detail. That's why I'm not going over that. This. And let's see if David remembers. Okay, HCl is one of your strong acids, right? Which means, what do we mean by strong? They break apart 100%. So that is a strong electrolyte. It's all H pluses and Cl minuses. Those charges are going to carry electricity. C6H6 is what? A coal? Ionic, covalent.
Covalent.
100% covalent. Things that are 100% covalent will never break apart. Never. They may have OH tails. This one doesn't. So it won't even dissolve, right? So forget it. It's going to be a non-electrolyte, right? What is this, Hannah? Ionic, covalent, polar.
Yeah.
How do you know?
Because there's this,
Metal and non-metal, right? It has NaAA, which means it's going to dissolve 100%. Strong electrolyte, right? It does have the Q. No, it's missing the H. So it doesn't have the Q. So, and what is this one? How do we, well, you don't know the name, but it does have the Q. It is a covalent molecule and likely has OH groups, but it is a weak acid. It's a carboxylic acid. The Q means it's a weak acid. Do you know what that is, the CH3COOH? It's vinegar. That's the other way to write it. We normally write it as HC. What? Yeah, we normally write it like that. 232. C2H3O2. But you could also write it like this. This is actually the preferred way for biologists to write it. I like that one better, but we use both in chemistry. Now, so gases, you need to think of Coke again. If you want to keep the gases, the carbon dioxide in the Coke, you need to have it cold in order to increase the solubility. Low temperature increases solubilities. High pressure, the can of Coke is always pressurized, right? So, and that is the pressure above the solution. It's important. You gotta have pressure to keep those gases. The carbon dioxide, the partial pressure of carbon dioxide must be is dependent on that. If you have very little carbon dioxide, more of it will tend to come, but if you have more carbon dioxide, you keep it in. So whoever did this is because you put the mass of the solute divided by the mass of the water. Percent is divided by the mass of the whole thing. So you had to add these two together, right? Mass of part divided by mass of the whole thing, not just the water. Molarity is divided by the volume of the solution. You know, some things are the solution, some things are the solvent. This one is the solution as well. You need to make sure you're understanding this because this is a study. It's not in your best interest and it's kind of brain dead to try to do something else because you're not engaged in what's going on. And this is a studying for free with the teacher. So if you decide to do something else, it's on you, but it's not a smart decision. So I'm gonna, I have to skip. So what you do when you have a mass percent, when I first read this, I got confused because I thought it was grams of NaF, but it's not grams of NaF, it's grams of solution. How many grams of solution is needed if you want 1.33 moles of NaF? What I find confusing in here is they're also asking for moles, and if we have mass percent, we're likely gonna find grams, right? So let's just focus on the grams and let's just make it what mass normally is. Mass percent is 2.34 grams of NaF, the solute, or the part, divided by 100 grams of the whole thing. So let's call it solution. Right? That's what mass percent is, right? Grams divided by the 100 grams, that is gonna be equal to whatever this is in grams. So, and they didn't give me the molar mass, I added it as well. So you have 1.33 moles of NaF. That is 1 mole. It's 41.99 grams. How much is that if anybody has it? What is it?
55. 8467.
So when you do a percent, this is what works best for me. There are many ways to do in a percent and they're all right. I put parts over whole of the percent. It's gonna be parts over whole. So this will be your grams, your mass of the solution, right? So your grams of solution. It's that ratio, and then I need to find the grams of solution. How do you do this? You take this to the other side. Grams of solution will be equal to 23.4 grams of NaF. And my 100 grams of solution over here, go to multiply over there. Grams of NaF and grams of NaF cancel, and I end up with my answer in grams of solution. There are many ways to do percents. I don't care how you do it. You may do it differently in your math classes. It's okay. Yes?
Wait, why did you take the 55.8 and put it like over there?
Because when I do a percent, every time I do a math problem with a percent, I always do, if I know the percent, like this is 23.4, that's what percent means, part over whole. And in a percent, the whole is grams. I make this equal to the fraction of what is it that I actually have. The part over whole that I actually have, and I have this many moles, which is really 55.4 grams, right? That is the part that I have. So I want to have a 23.4%, so I need to make that equal to my parts over whole of what I actually have. And what I actually have is 55.4 grams. So what ratio to what grams of solution will give me that? So I find this. I have to find the grams of solution. This division must be equal to 23.4%. So that's how I found what the total solution, total grams of solution were. Very, very, very important. All math can be solved like this. And when I used to teach physics, this helped people way more than many other ways. It's easier. You're comparing, and it's part over whole, and you find your whole thing. Now, next one. So they gave you volume, they gave you molarity, right? What can you do? Boom, will give you the number of moles. You take those moles to grams, and you weigh that out. Then you dissolve it, and then you add the rest. It must be 21.2 grams when you do that, and then multiply by the molar mass. Those are moles, so this will be grams per mole. You get the grams, you put them in your container, you put a little bit of water, dissolve it, and then add it until you get to the final volume. Right?
Final volume of 2 liters.
Yes. Yeah, that would be a big one. This is 1 liter, so it'll be a really mambo jumbo one. But they're used, again, this is a study, so you don't have to study at home. Oh, that's the right one, sorry. I thought that was the wrong one. Yeah, if you have BCl2, that dissociates into Va2 plus 2Cl2. So if you have one of these, you have two of those in solution, right? If you have one of this whole thing, you have two of those in solution and one of those in solution. If I have a dozen of these, I have 12, then I have 24 Cls in solution. Does that make sense? Everybody? Hopefully recording these and doing it like that helps everybody out. So this is a boom boom one, right? Simple, you just solve for the unknown. Yellow must have marked something wrong. Does anybody have questions on this? That you can definitely expect to have. So this one read a lot more, but I simplified it so I could write it, and Kahoot will let me. But they basically have this. You have the molarity and the volume, molarity and volume. The volume we don't know of H2SO4. The molarity is going to be 0.755. The molarity of the KOH, 2.5 moles per liter, and the volume is 55 milliliters. So you do boom boom, and I'm gonna tell you, this is not a dissolution. This is not a dissolution. You're just trying to see, you have volume of the base times molarity of the base is equal to volume of the acid times molarity of the acid. This is a neutralization. Vm is number of moles of the base. This number of moles of the acid. When the number of moles of the base equals to the number of moles of the acid is when we neutralize something. Does that make sense? This is not a dilution. This is not a dilution problem. And the other thing is, very, very important. I'm glad this one had it. You have to do 1 over the number of moles, 1 over the coefficient of my base and 1 over the coefficient of my acid. The coefficient of my base is at 2. So I should have a 2. This is the hardest problem in the whole Kahoot. Simply because you may have seen it in mastering chemistry, but we really had not talked about it as much. But we're talking about it now, yes. Because the formula for dilutions actually tells you how many ions you have of it, and in this case, you have 2. It's 1 over the coefficient and 1 over the coefficient. That's what the formula should have. All the dilutions we do, we have 1 as a coefficient, so we don't ever care, right? But in this case, we're trying to find, we have 1/2, so we have 2 KOHs for every H2SO4. So the formula really has 1/n divided and 1/n. In this case, is 1/1. That's the reason we never write it. But if you look at the formula in our study guide, it does have to do with that. But we always have a 1-to-1 ratio, and we will always have a 1-to-1 ratio unless we have a neutralization. Sometimes we'll have different ratios, and I want you to pay attention to that. Everybody's okay with that? Are we okay with that? It is not an unfair question because it's the exact same thing we've seen, it's just a different application. So this is the one that normally gets people. They think that it depends on the type of solute. As long as you put a stuff, it is going to increase and decrease. Increase the boiling point and decrease the freezing point. You don't, it should dissolve. It should be a part of the solution. But besides that, you can put anything and it'll do it. To what extent? That's a different story. But that's the one that people normally get caught on. To freezing point of a solution is lowered by the addition of a salt, is asking for false, right? It will always decrease the freezing point and it will always increase the boiling point. 2 more. A Kahoot should never be more than like 12 questions. Okay, this is an important question because it has to do with intermolecular forces. What is the name of this? I haven't asked questions. Fairfax, what is the name of that? That's literally remember? Caldwell? That's the first one. Methane is CH4. It's methane, ethane, propane, butane, and all the others, right? It takes everything. Believe me, it takes forever to learn them, but try to learn them. So this is a hydrocarbon, which is what's important, which means it's 100% covalent, which means that the intermolecular forces between this one and another, because carbon-hydrogen is always 100% covalent, what would be the name of the intermolecular forces between these two compared to if you have methanol, in which you have with an OH. So what is the name of the bond these can bond within each other, you know, they can be hydrogen bonds in here. If you have OHs, you can have hydrogen bonding. If you have these ones, what's the name of this intermolecular force, Brennan? Between these two, what's the name of that intermolecular force? It's two 100% covalent molecules. It is intermolecular. What's the name? Autumn. It would be, but it is an instant dipole. So what do you call instant? London dispersion. These are instant because they don't have a pole. These are non-polar, right? non-polar. And non-polar can only have LDFs, right? It's the weakest. The bigger, the more the charges that can happen, because at some point, these ones, all the electrons are gonna be on this side, and they will attract each other. But the bigger it is, the bigger the charges. So these are instant dipoles. They're non-polar, but they will have instant dipoles. Now here you can have London dispersion between these two, but you can also have hydrogen bonding. What about, oh, that was it. So which one has the strongest? The one that has hydrogen bonding and London dispersion, right? Hydrogen bonding is the second strongest intermolecular force. Those intermolecular forces will dictate the melting, boiling points, and all those. You know how long it takes me to find these things that I like? I really shouldn't put them, but I'm like, that is so cute, I need to put something. So yeah, we're struggling in this one. If you have, do ionic, is this ionic? Yes, right? It's a salt. And this is an ionic salt as well, right? They don't have intermolecular, well, they have London dispersion forces. Everything has London dispersion forces. But besides that, they are ionic, which trumps everything, right? So you have an ionic bond and you have an ionic bond. That would be the equivalent of an intermolecular force in a salt. So those are the biggest, humongous boiling points. Now that one has more electrons, it's bigger, it's gonna have a stronger one than this one. Can you see how this one is smaller than that one? So that one will have more. However, between these two, which one will have the highest boiling point that you think? If you had to think about, you have an HCl bonding to another HCl. What type of bond is that one? And then you have a sugar molecule bonding to another sugar molecule. Which one do you think will have the highest boiling point? This is full of OHs. Full of OHs. This one has that one. What is the name of this intermolecular force? Baby, what's the name of this intermolecular force? No, covalent is polar covalent right here. No, these are not non-polar. These are polar. This is polar, and it's a permanent dipole. They are both polar molecules, right? They're not like instant. That's London dispersion. Normally, they will have London dispersion, but there is also two polars. What do they call two polars, David? Dipole, right? So this is a dipole because it's polar, so it has two poles, so it's a dipole. That's that force. This one, what's the name of this one between the OHs? Hydrogen bonding. I will suspect, I haven't looked, that's big, so it has London dispersion forces that will be bigger than any that this one can experience, right? Because it's a humongous one. Sugar is a big old molecule. C12, 12 carbons, so it's 22, so da-da-da. And then it has all this hydrogen bonding. It actually makes a crystal, it's solid. They're so strong, it's solid. I would think this one has stronger London. You see, woman, you can't get distracted, Hannah. Otherwise, then you'll be like, I didn't get that. But this is important. We are explaining it. Last one. I know 15 is a little bit too much, but Rich, you stayed on top. We did this lab, similar. Three people out to lunch. We had the egg on one side. That's not an egg. Let me draw a better egg. We had the egg on one side and we had the solution on the outside. Right? In this case, one of them has 0.1 molar and the other one has, well, this is not an egg, this is two solutions of sugar. One is 0.2 molar, let's say here, and this one is 0.1 molar, right? They have a semi-permeable membrane, right? Who was next? Sophia. What direction does the what? Okay, so what direction does stuff flow? Does the sugar go through the semi-permeable membrane? Or, no, you can't. That's the reason osmosis has to happen. Because the sugar is too, it won't go through it. It won't go through the membrane of the egg. So you have to, what? It goes in the direction to dilute, right? This is more dilute than that one, right? So it'll go in the direction to dilute. Everybody okay with that? Osmosis goes in the direction to dilute.
So water moves from the 0.1 molar to the 0.2 molar, which
Yes.
makes the first solution more.
Which is going to shrivel this thing, and it's going to, the water will be escaping, right? That's kind of like when you start eating too much salt and all of a sudden you have a hypertonic solution outside your cells and you can die. But again, important concept for you to know, this is more for biology than it is chemistry. I mean, it is chemistry as well, but
So it flows from like the less or
less, it goes in the direction to dilute, so it goes towards the most concentrated. The one that makes sense